All right, so no doubt you just finished section 23.3 of the lecture, and it is arguably one of the most confusing sections. And the reason, especially if you're watching it digitally, is because you don't get to see it. You don't get to see what's physically happening. You're just taking me talking to you and taking that for my word. And in class, I spend some time to actually physically show you what's going on. So the next best thing that we can do is a lab that helps us hopefully see this and understand it. Now, again, we're using a simulation, but this will hopefully kind of make sense of stuff. So here's the lab. And again, normally in class, we'd use batteries and light bulbs, but instead we are going to, again, use our simulation to make it nice and easy. And let's jump back down to lab 7.9. I do have, you're setting up this circuit. You're setting up a circuit with two light bulbs in it. Very, very, very simple. And you draw a schematic diagram. You can use, I have an online circuitry thing built here, which allows you can see on the left hand of the screen, it gives you a bunch of tools to use. You can use that. There's also, if you're familiar, if you do 3D printing, you're familiar with Tinkercad. Let me go ahead and I think I have something here. We'll choose one of my many logins. And Tinkercad is another way that you can sketch some circuits. So you can mess around with Tinkercad circuits and do essentially the same thing. So it kind of gives you some stuff right off the bat, but you can get the battery in there, the resistor, whatever. So you can make these circuits, and instead of using a regular like pictures, you can actually start simulate what goes on with this circuit. So feel free to take a look at that. Feel free to take a look at the circuit construction kit, or just draw it out, because that's all you really need to do is draw a simple schematic or the drawing tool. So let's go here and let's make this circuit. We got a battery, and it says to use 3 batteries and a battery pack. So 3 batteries would essentially give us a voltage in real life of about 4.5 volts. Since we have 9 volts here, let's just stick with that. So 2 light bulbs connected in series, and you kind of just play around them a little bit, but there's that. Go into there, connecting it to there, and finally, there is our complete circuit. Now, cool thing about this simulation is that you can, on the right side over here, that's got a picture of a battery. That's the schematic. So here's the schematic of the simulation. Both are good. And really what we're looking at is looking at confirming everything that we learned in section 23.3. So I have the circuit it's made, and it tells you, so this part A, B, C, D, E, and F, get the voltage across each of the parts of the circuit. So if I bring my voltmeter here, going across A, so where am I? I'm at point A. So from A to F, that's across the battery, right? A to F, boom, 9 volts. It says negative 9 volts. Why does it say it? Because the red and the black have specific directions, and it doesn't really matter. All we care about is the 9 volts. What about from A to B? So that's just going across this wire here. So I go from A to B. I go, there's my B, there's my A, and I get 0 volts. Why is it 0 volts? Because we assume that wires are ideal wires, and there's no voltage drop across the wires. So you're just going to use the multimeter to get the voltage drops. And then the question is, how does the voltage drop of the battery compare to each of the components? Well, according to series circuits, I should get those voltage drops to add up. So A to B is 0, but look at this guy right here. Going across this light bulb, that's 4.5 volts. Going across this light bulb, that's 4.5 volts. So 4.5 and 4.5 give me my 9 volts. That's a series circuit. Now, part 2, very simple, especially since we're doing the online version. It says put the ammeter in place in 3 different places by in the circuit. So really simply for that, we're going to get rid of the voltmeter. We're going to grab our ammeter. Now this circuit tool, this construction kit, makes it super easy. I'm just going to put it here, 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 and what do I see? The lamps should all light up. What happens? Well, 0.45 amps, 0.45 amps, 0.45 amps. The current is the same no matter where it is. Why? Because the current is the same throughout a series circuit. All right. Last thing is we want to take our multimeter away and remove the battery. So let's remove the battery. Let's get rid of it. And the last step is to use a multimeter to determine the resistors or the resistance across. Now, unfortunately, in this simulation, I do not have that capability. So instead, we're just going to take a look at, when we're taking a look at the resistance, and again, we'd use a multimeter to do this. Well, I have a current, if I were to click on this light bulb, or I have a resistance rather of 10 ohms and another resistance of 10 ohms. And if I put my battery in there again, I knew that with my 9-volt battery, I had 0.45 amps of current. So 9 volts divided by my 0.45 amps, I get 20 ohms. What does that mean? It means that my 10 ohms here plus my 10 ohms here gives me a total of 20 ohms. And that makes sense because resistance adds in a series circuit. So bulb 1, 10 ohms. Bulb 2, 10 ohms. Bulb 1 and 2, 20 ohms. So that's what should be true for a series circuit. And that's all it is. It's a quick walkthrough. Again, I probably just did everything for you right now, and you didn't need me to do that. But since we're not doing this in class with the batteries and light bulbs and the actual multimeter, it makes the lab super quick. But I hope that you get some of the concepts and what are true with a series circuit. Now, the next lab, let me go ahead and grab my battery again. Here's my series circuit, right? Super simple series circuit, okay? We're going to set up a similar circuit, except instead of course, being in series, we're going to be setting up these light bulbs in parallel. So I'm going to do that, and I'm going to have one complete circuit there, and then I'm going to branch this off, and I'm going to have another complete circuit here. And boom, that is a parallel circuit. It might be a little hard to see because these wires are so ridiculously close together, but we're going to analyze the parallel circuit. So lab 7.9 was writing a series circuit. Let's jump right into lab 7.10, wiring a parallel circuit. And I like to keep these two side by side because it really helps us understand some of those concepts. So I set up the circuit, draw a schematic diagram to see what's happening. What happens when the second bulb is added? Well, the second bulb, I can even verify that by clicking it out here. This is the first bulb right here. Right here, this is my first bulb. What happens when I connect the second bulb? Boom. And the answer is nothing. Nothing happens when I add that second bulb to the first bulb. It's just as bright. So how do the brightness compare? Those brightnesses are identical. Now let's go ahead and let's use the voltage. Let's get the voltage across the battery. So we got my voltmeter, voltage across the battery, and we already know that that should be, boom, 9 volts. What about the voltage drop across each of the light bulbs? Look at that, 9 volts, and guess what? 9 volts. Now, as I mentioned in the lecture, that seems to violate Kirchhoff's loop law. And really it doesn't though, because the loop law states that the voltage drop across an entire circuit is 0. So let's follow a loop here. On the left side with the series circuit, 9 volts, 4.5, 4.5, 9 minus 4.5 minus 4.5, I'm back to 0. On the circuit on the right, 9 volts, back to 0, or 9 volts, all the way over 9 volts, back to 0. So it does not violate Kirchhoff's loop law. There are just two different loops going on with this circuit. All right, so with my lab, the battery, 9 volts, bulb 1, 9 volts, bulb 2, 9 volts. They're all the same. All right, now let's take a look at the wiring into a toggle switch so that only bulb 2 turns on and off. So now you're kind of problem solving a little bit. How do I get bulb 1 to stay on and bulb 2 to turn on and off? Well, if I think about it, I got to break up this part of the circuit. So let's go ahead and let's break up this part of the circuit because that's what I care about. And what I can add on the side over here, I have a switch. And a switch allows a light bulb to turn on and off or to stop the flow of electrons. When I close that switch, take a look at that. It pops on, pops off, pops on, pops off. So we can use a switch to turn a bulb 2 on and off while bulb 1 always stays on. And you're going to go ahead and draw a schematic of that. Then do the same thing so that bulb 1 turns on and off and 2 turns on. And then skip question 6 because we don't have variable resistors. But a variable resistor potentiometer is a way to manipulate, and I'm just checking that I don't have a rheostat or a potentiometer, and I do not. It's a way to manipulate like the brightness. So think about like a dimming switch. So go ahead and let's just skip question 6. All right, and finally, we're going back to this concept of current. And we want current and resistance. So we want to get the resistance. So both bulbs, that's 10 ohms, and this one is also 10 ohms. So taking a look at what's going on with the resistance, well, if this isn't here, so what's going on with the resistance? So I can't measure this directly, but let's go ahead and take a look at this current. And the current is 1.8 amps. So it's got a lot more current than over here where it's only 0.45 amps. So I know that there's something different going on. And what has to be my current, or my resistance, I'm sorry. And I got 9 volts divided by my current of 1.8 amps. And I got a resistance of 5 ohms. 5 ohms, that's it. So this was 10 ohms making 20 ohms. This is 10 ohms making 5 ohms. So bulb 1 is 10 ohms, bulb 2 is 10 ohms, 1 and 2 is only 5 ohms. And finally, we're going to take a look at the multimeter. And my ammeter right here says 1.8 amps. And going into this branch, it's 0.9 amps. And so these two branches are 1.8. So it's 0.9 amps going across this light bulb and 0.9 amps going across this light bulb. And that validates Kirchhoff's junction law that the current has to add up. So it's 1.8, it's 0.9 here, 0.9 here. They're each getting half of that total current. So that should help you out right there. And that's going to be it. So that'll kind of walk you through that last part in part 3. I know this was somewhat of a longer video. I'm sorry, but I went through 2 labs in less than 15 minutes, and now you have everything you need to do labs 7.10 and 7.9. And again, hopefully you can see how this series circuit and this parallel circuit all kind of compare. And again, I guess I could make this really easy and add another circuit right in the middle here and say, what about just one light bulb? Let's do that real quick. Let's spin this guy around. There's my one light bulb. Perfect. So I see that if I have 2 light bulbs in series, the light bulbs get less bright. Here's my run just by itself, and then 2 light bulbs in parallel. They're equally as bright as 1 light bulb in series. There's a lot of stuff going on here, but what do we notice the most? Look how slow these electrons are flowing. This going slightly faster. And look at how these electrons are booking it compared to the other 2. And that's because this battery right here is sending out more electrons because these 2 light bulbs give it less resistance. So this battery, if I look at these, this one's going to burn out quickest. This one's going to burn out next. This one's going to burn out last. So these different light bulbs combinations are going to have different effects on the battery as well. And that might be a conceptual test question comparing some circuits together and to see what's going to happen. So that's it for Lab 7, 9, and 710. As always, let me know if you have any questions. We just got one more lab that we're going to be taking a look at, and it's a puzzle, so it's fun. All right, but we'll do that after complex circuits. So one last section to go in this unit. Let me know if you have any questions.